for coming to my talk. I'm Zeyu from MIT. So today I'm going to talk about something about offline reinforcement learning. And this work is a joint work with my advisors, Sasha Rocklin, and Ayush Zachary, and Chen Yu Wei. So before coming to the details, let's first recap of what the reinforcement learning settings we considered. So we considered this finite horizon Markov decision process. And this consists of 6 element tuples of the state space, the action space, the transition model, the reward function. And this H denotes like the horizon or the number of steps during the interactions with the environment. And also rho denotes the initial state distributions. And among these terms, this transition model, the reward function, and also the initial state distributions are all unknown to the learner. So normally, the learners interact with the environment using this online interactions ways, which means like the learner at every step submit an action to the environment, and then the environment will return to the learners the next state, which samples according to the distributions, the transitions, and also a reward function sample from the reward functions. But sometimes, in some environments, actually the learners cannot interact with the MDPs or the environment directly. Instead, we'll consider this setting where we call the reinforced learning with the offline data, where at each step, a state action pairs sample according to a given distribution mu. This is the distribution we call the offline distributions. This state action pairs is submitted to the Markov decision process. And after that, the Markov decision process will return the next state sample according to the transition model and the reward function according to the underlying transition model and the reward function. So this is a model we considered called the reinforced learning with offline data. So this mu is what we know as the offline interactions or this offline distributions. And this SH+1 and RH is what we call this offline data. And our objective in the previous online reinforcement learning is to optimize the value functions, that is, trying to find a policy pi, which satisfies that this value function of the policy pi is close to the is actually being optimized or achieving to be the largest among all the policies. But sometimes we usually consider a simpler setting where we call the policy evaluation. So in the policy evaluation, actually the learner is not trying to find the policy pi, which has the greatest value among all the policies. But instead, the learner is given another policy pi e. This policy is something like what the learners actually trying to interact with the environment, and they try to know that actually whether this policy pi is a good policy or a bad policy. So in this policy evaluation settings, the learner's objective is trying to estimate this v pi for a given policy pi as accurate as possible. So let's group these things together. So we come to our settings where we call the offline policy evaluations, where the learners is given the offline data, where this offline data is generated according to this offline distribution mu, and also this RH and SH+1 is sampled according to this underlying reward model and the underlying transition model. And then the learner is also given the policy to be evaluated, where we denote as this pi e. So on top of that, the learner is also given a function class, where we assume that this function class is realizable. That means like the policy pi e's q functions, q pi e, is lies in this function class f. And this function class f is usually not very large. So that means like maybe something like the log the size of the f is can be tolerated actually in this complexity. And after given these 3 pieces of information, the learner is trying to output this v hat, which is a value function of the policy v pi e. And we use the expected value between this v hat and the v pi e to denote like actually whether this evaluation is successful or not. So our objective is that how many samples do we need to sample according to this offline distribution mu to estimate or approximate this V pi e with maybe high probability. So this is the objective of the offline policy evaluation. So any questions so far? What we're trying to do is under the expected version, or maybe we can call it maybe a L1 version. So it's like the expected of the this v hat minus v pi e of the absolute value, and we use this denote as the error of the approximation. So it's somehow like the L1. Okay. Yeah. So for this offline policy evaluation, one quantity which is important to us is what we call the considerability coefficient. So this considerability coefficient is a popular notion in a lot of previous RL literatures, and this captures actually how much does this offline distribution mu covers the policy pi to be evaluated. So this is defined to be the supreme over the density ratios of the state action pairs. Like we usually consider two possible considerability coefficients. The first one is the single policy considerabilities, where we only want the offline distribution mu to cover the occupancy measure of the policy to be evaluated. That is, we require this supreme over state action pairs of this density ratio between the between the policy to be evaluated and these offline distributions to be bounded by some given constant. The next thing is a more stronger notion where we call it the all policy considerability. In this notion, we require that this offline distribution mu covers all the policies, all the possible policies. So this we require this. This is over. This is upper bound for the coverage actually with respect to any possible policies. Yeah. So the next thing is like previously we mentioned, this data is generated according to some distribution mu, and this is what we call the offline distributions. But sometimes, if we have assumptions on the data that is actually we have more structure on data, maybe this is more benefitable to the learners so that they can learn maybe the approximate the value functions more easily. So one possible assumption is what we call the admissible data. That is, we assume that there is a policy that is what we call the policy to collect the offline data. This policy pi b, every time we'll just collect the samples ISH, AH, these state action pairs according to the occupancy measures of this policy pi b. And this is what we call the admissible data. The next notion is even stronger notion is the trajectory data. That is, we assume that not only we can collect the state action pairs, but we can collect the whole trajectories with respect to this policies for the offline distributions, this pi b. So every time when we collect some data, we just generate a single trajectory from the first state to the state in the h steps. This entire trajectory is given to the learners, and the learner can use this set of trajectories to approximate the value functions. So definitely, this trajectory data contains more information than the admissible data. So, and we will ask the following questions. So suppose that we have this considerability coefficient. So and given this function class f, can we have an absolute accurate evaluations using the polynomial number of offline samples? So here, this absolute accurate evaluations means like in the L1 sense, that is the expected of the absolute value between the value functions, the true value functions and the approximate value functions. So this is how we define this absolute accurate. And we also want to ask like whether the admissible or trajectory data can help the learners to get maybe some algorithms so they can be polynomial sample complexity. Yeah. So any questions so far? Okay. So next, let's recap some previous existing literatures. So this is also some another work that's focused on the offline policy evaluations. This is Foster et al. 22. It shows that actually with a realizable function class, and we assume that the concentrability coefficient is small. So if the data are sampled according to a general distribution, a general offline distribution mu, then we have an exponential lower bound on the sample complexity. So that means like this is usually not achievable. And the next thing is like they also show like if the general data, actually the offline data is sampled according to some admissible distributions. But here the admissible distributions is only the first two steps. I will specify this in the next slide. They also show that there exists an exponential lower bound on the sample complexity. And the last thing is some positive results. They define this notion called the strong coverability, or it's also called the push-forward coverability. It shows like if we assume this realizable function class, and we assume that this strong coverability thing, then with general offline data distributions, then there exists polynomial sample complexity algorithms. And this algorithm is called the batched value batched function approximation tournament. And actually, we will refer to these algorithms later. Yeah. So next, we'll specify what's the difference and what's new compared to our results to the previous two results. This is also lower bound results. So to this Foster et al. 22, actually, one thing they consider is they consider the discounted MDPs, and they assume that the data comes from some offline distribution mu. And the next thing is they consider this admissible data, which is some data that only being admissible for the first two steps. This algorithm is for the policy optimization, but it can also do for policy evaluation as well. Yeah. Yeah. So here, actually, we assume that, or actually in there, this Foster et al. 22, for the first thing they assume is discounted MDPs. And they assume that the data comes from some offline distribution mu. The other thing is they mentioned that their results can apply for the admissible data. But here, this admissible data is somehow only consider the first two steps. Like actually, we can show in the left figure, like they only consider like from the first layers. If we run this policy pi b, which is a offline policy to collect the offline data, if we run this pi b for two steps, what's the next steps distributions? This is serves as admissible data in their paper. The step actually in our paper actually we will mention that our results is holds for this finite horizon MDPs, but in their results in this Foster et al. They consider the discounted MDPs and they just run this policy pi e for two steps. Like you can see that actually we can translate from this. These are not necessary to be maybe the first layer, second layer, third layers, but instead they can translate from the first layer to that state to this state, and they consider this admissible data to be, we just run this pi e maybe for two steps, what the distributions or the occupancy measure of pi b looks like. Yeah, in our results, we consider this finite horizon MDPs. It's not finite horizon. Yeah, the thing is that actually in their MDPs, the first thing is like all the states are being reachable within two steps. The next thing is like to get this admissible data, if we go back to the definitions, we require this offline distributions mu h to be the occupancy measure of pi b somehow. And here, this occupancy measure of pi b in their paper, they define this to be the occupancy measures if we take this pi b for two steps. So what's the data? What's the state distributions in this among all the states looks like. Yeah, exactly. Like for the admissal data, here actually the admissal data cannot be maybe be grouped together. Like actually every steps, maybe for the first step, S1, A1, R1, S2 prime. This is for the first step, and for the next second step is S2, A2, R2, and S3 prime. So actually these two admissal data we cannot group them together. But for trajectory data, we are assuming that this trajectory is sample from the first state to the last state, so we can maybe just group them together. We can obtain a complete trajectory. Yeah. So any other questions? Mm-hmm. These are the same papers. The first. This one. Mm-hmm. There's a circle. There's no circle. Yeah. Actually, we can transit from any states to any other states. There can be circles, but we didn't show it. Yeah, in this. Yeah. After two steps, the transition is still not terminated. Actually, we can transit to the third steps or in the fourth step, but these transitions are no longer considered in their admissible data. So normally, actually, no, yeah, I can specify this. Yeah, so we know that actually this mu this offline distribution mu in the admissible data setting is something like the occupancy measure of the policy pi b. So we can define this first step occupancy measure is like we start from the initial distributions. We take one step according to pi b. What's the next offline next state's occupancy measure? This is what we call the first step occupancy measure. And the second step occupancy measure is like we take two steps according to policy pi b, what the state distributions looks like. Yeah. Not the general admissible data. They don't run this trajectory. Maybe for the data that are collected according to the third step, this distribution they are not included into this admissible data they consider. No, actually, it's not general offline data. So they only assume that the data are sampled according to this first two steps admissible data. So there's no other data. Yeah. Right. Yeah. Exactly. Yeah. Okay. Yeah. So so that's also the reason why there's some maybe limitations for their two results. So that's motivations of actually our research is trying to put this for finite horizon MDPs and admissible data apply for the entire trajectory, this H steps. So this is our first result. And the second result is whether this trajectory data help. And we also want to show like actually if this all policy conservability coefficient is not the correct thing to correct this offline policy evaluation problem, so what's the correct thing to characterize this? So our contributions is like we first proposed a new measure where we call the aggregated considerability coefficient, and we'll develop a lower bound in terms of this measure. And thanks to this aggregated considerability coefficient, we can prove an exponential lower bound for this admissible data, and this admissible data is for the entire H steps. And we also have an exponential lower bound for trajectory data. So that means like the trajectory data doesn't add too much to the offline policy evaluation problem. And finally, we'll present an upper bound on the sample complexity, showing that actually if the aggregated considerability coefficient is bounded, then polynomial sample complexity is achievable for offline policy evaluation. Yeah. So, any questions so far? Actually, this thing is it's always finite. Maybe we consider this MDPs to be maybe finite state actions, so it's always finite. But if this this aggregated considerability coefficient is extremely large, like if it's 2 to the h, then we have a lower bound for 2 to the h. Yeah. If this aggregated considerability coefficient is maybe h squared, then we have a polynomial algorithms for that. Yeah. So we'll go into the definition of this aggregated considerability coefficient first. So we first define the aggregation scheme. Suppose there's a MDP, and this is the H layers. And we'll group the states within each layers into some groups. This group is what we call the aggregation state. And this method of group, this how we partition each layer into several groups. This is defined to be an aggregation scheme phi. So as you can see that actually these rectangles, it denotes a possible aggregation scheme. But actually, one thing for this aggregation scheme is like we require within each layers, the aggregation scheme cannot do across layers. So we cannot group this state and this state. So it has to be within each layers. And after we define this aggregation scheme, we'll define something called the aggregation transitions. So this aggregation transitions is a transition over aggregated states. So suppose this is transitions for the original states, and after we do this aggregation, we'll construct the transitions for the aggregation states, which defined to be the weighted average of the transitions among the within each aggregations. And we'll show that this thing, aggregated considerability coefficient, is defined to be the considerability coefficient with respect to this aggregated transition T. So basically, suppose this is V1 is aggregated states, and we use this D bar V1 to denote the occupancy measure of this aggregated states under the transition model T bar. This T bar is the aggregated transition model. And we use this offline distributions of this aggregated states V1 to be the sum of the states in it with some of the occupancy measure under mu for the states within this aggregation scheme. And this aggregated considerability coefficient is defined to be somehow the largest ratio between this D bar and over this mu. So, and here, notice that we require that this, we also require that this sum of the occupancy measures under the aggregation states is greater than epsilon. So this conditions is somehow used in the proof of the used in the proof so that we can get maybe epsilon accurate evaluations. So, but generally, you can view this as occupancy measures or the considerability coefficient in the aggregated transitions. This aggregated transitions is defined here actually as the weighted average of the transitions. Sorry. This mu is offline data distributions. So this thing is given to the learners. Like if we go back to this, so we'll know that actually this data generation process is that this offline distributions, this S and A, are somehow according to this mu. This one? Oh, capital phi is just like this, this gray rectangles. This is denote the aggregation scheme. So this is one way to aggregate the states maybe within layers together. subset means like maybe this phi can connect maybe this state, and this state. So this is a subset.
Okay, so you're taking a subset of the state group.
Yeah. Yeah, and we take the maximum over all subset so that this occupancy measures, this aggregated occupancy measures, sum of the occupancy measures is at least absolute. Yeah, we can understand that. Mm-hmm. Yeah, exactly. Yeah, because we can build those subsets whose occupancy measure is that thing is a larger version compared to this definition, but you also incorporate those phi, which is very difficult to arrive. So that those phi, we can just ignore them, even though that the offline data distribution doesn't cover those aggregation states very much. So this why we need to maybe sum of these occupancy measures to be greater than absolute is like we want those aggregation states or the states within those aggregation states, they will maybe make a huge difference into the value to be evaluated. So we don't want actually this only contributes very little values. So that's why we require these conditions of this at least the absolute occupancy measure. Yeah. So any other questions for this? Yeah. Okay. Yeah. So after this, we'll give the lower bound for general data. So suppose we are given DPM and also aggregation scheme phi and this offline data distribution mu and also evaluation policy pi e. We can construct another family M such that the value functions contains only two Q functions, and this F is also realizable. And here we also require this F is compatible with phi, means like these Q functions for the states within each aggregations are all the same. And we also have the all policy considerability coefficient is of the same order of this MDPM, and the aggregated considerability coefficient is also the same order of the MDPM and mu and this aggregation scheme phi. So that any algorithms that can do O1 accuracy offline policy evaluations must query at least this number of samples, this aggregated considerability coefficient number of samples for at least one MDP in this class. Yeah. So any question for this? Yeah. Mm-hmm. This is because like if we don't do this sum, then maybe there exists some phi which is the occupancy, both the occupancy measure and this offline distributions, they are all very small. So we can just ignore these states because actually this state is very difficult to reach. So it doesn't matter whether this state is covered very good or not. Yeah. And if we require these conditions, then we know that actually there exists at least maybe a group of states. So actually this occupancy measure is at least absolute. So they will make a huge difference to the value functions to be evaluated. So that's why this C bar is a correct notion compared to the not restricted version. Finally, we'll show that actually this C bar definition is also there is also an upper bound, showing that actually if this C bar is maybe small, then we have a polynomial algorithm. state. Yeah. The learner is not interacting with the aggregated states, it's interacting with the original state. The aggregation scheme and the aggregated states and even the aggregated considerability coefficient, they are all served as some media. Like we use these terms to construct the lower bound, but the learner does not interact with them to get, maybe directly. Yeah. Yeah, exactly. Yeah. Yeah, it's playing with the original MDPs, but the original MDP's considerability coefficient is not the correct thing. I will show that this considerability coefficient for the aggregated MDPs, this is the correct thing. You can characterize both the upper bound and lower bound for this offline policy evaluation task. No, this fee is given to the upper bound. In the upper bound, this given the function class f, actually this function class f will define an aggregation scheme phi, because actually the aggregation scheme will require that this f is compatible with the aggregation scheme, means that within each aggregated state, the f's value are the same. Yeah. Yeah. You mean the Q star? Yeah. This thing is for policy evaluation. It's not for policy optimization. Yeah. Previously, we tried to use this type of thing to construct lower bound for policy optimization, but it doesn't work. Yeah. Yeah. Right now, actually, this result is only used for policy evaluations, and this is a very good open question. It's like whether this type of aggregated considerability thing can apply for the policy optimization task. Yeah. So if you only want to remember one thing from this talk, is that the sample complexity of the offline policy evaluation is not bounded by the standard considerability coefficient, but instead is bounded by the aggregated considerability coefficient. Yeah. So this aggregated considerability coefficient is the true quantity that can capture the sample complexity. So, yeah. For any MDP. Yeah, this is MDP M and aggregation scheme phi and the offline data distribution mu, and this evaluation policy, this can be arbitrary. You can say something like that. So this thing is adapts to the MDP. This considerability coefficient adapts to the MDP. Mm-hmm. Yeah. So next, let's go over the construction steps. So the first thing is like we construct the aggregated MDPs, this M1 and M2, over the aggregation states. Let's recall this aggregated considerability coefficients definition. We know there exists this subset I of the aggregated states, so that this occupancy measures sum is greater than epsilon. So we'll use this I star to denote the scheme that attains the maximum. And for those aggregated states, which is within this I star, we will assign the reverse epsilon over h and epsilon minus epsilon over h for this M1 and M2. And for the states which is not within this I star, we'll assign the reward 0 there. And for the transitions, we'll assign the aggregated transitions to be the aggregation transitions we defined previously for this aggregated MDP. So in this way, we constructed this M1 bar and M2 bars over the aggregation states. And next, we'll use this M1 bar and M2 bar to construct this MDPs required. Yeah. So next, we'll construct the modified MDPs, M1 and M2. Suppose this is the original states, then how we aggregated them together. And for each layers, we add 3 more states, UVW. And we assign the transitions and the rewards in this way. So the UVW always goes to the W in the next state with a reward +1, -1, or 0. And it never goes to any other states. So based on these transitions, we know the UVW's value functions is +1, -1, and 0. And next, we will assign the reward functions for the previous states. So for those states, that's for those aggregated states, which belongs to this I star, we will assign this reward function to be f over h. For any other states, we will assign the reward to be 0. And for the transitions, we'll adopt the previous transitions of the MDPM, and we'll give them diluted transitions. That is, actually, we will dilute the transitions to be 1 minus 2 over h of the previous transitions, and we'll assign the rest of the transitions to the U and V in the next layers. And how we assign these transitions is like we have to make the value functions of the states to be within each aggregated states to be of the same value. So we can show, like, actually by some maybe complicated calculations that this is doable. And actually, after we do this calculations, we can show, like, actually this M1 and M2, they have a very important properties, like the value function of M1 and M2 differs by C bar times this epsilon. So that's how this C bar comes into the bound. And the next thing is, like, we'll lift this previously constructed this MDP M1, M2 into the rich observation MDPs. So for every state, we'll lift this state to the rich observations. So in terms of we construct a rich observation state X, the state space XS, and we'll make the transitions of the rich observations depending on this the latent states. And this is the transitions is denoted as uniform over the rich observations in the next states, and the reward function is the same. No, actually, this 3 replicates. This is for the each layers, and this UVW will also lift them to the rich observations. So this lift to rich observations step is what we did for every state in the layers. This is also include this UVW. We don't change the dynamics, so that means, like, the value functions are the same. But the thing is, like, based on these rich observations, we'll never see the rich observation state again. So that means, like, this will create some maybe difficulty to identify which state we have already visited or which state we haven't visited. Yeah. So any other questions? So this is how we define this transitions and the reward for the aggregated states, and for the rich observation states. So based on this construction, we will show that this is indeed a hard case for the learners to do offline policy evaluations. So why this is a hard case is basically because the learner cannot tell the difference between the rich observations. So that means, like, for any 2 states within the same aggregation scheme, within the same phi, within the same aggregated states, they'll be of the same values. So if we haven't visited this 2 rich observation states, we'll never tell the difference between them. So we cannot tell that this state comes from maybe some S or comes from some S prime. And since the learner cannot see the same observation state again, so we don't leave the learners some chance to distinguish that this state between belongs to the latent state S1 or belongs to the latent state of S2. we'll create to be maybe extremely large, like we can do maybe 2 to 200. Actually, this thing doesn't hurt the considerability coefficient or aggregated considerability coefficient. So we can make them infinite if we want. Yeah. Yeah, but just to maybe make things simple, we could just make them finite by extremely large. Yeah. Oh. Yeah. So, but we remember that actually among the construction, we also have some aggregated states within this I star where the values or the rewards between this M1 and M2 are different. So that means like if we arrive at those states, then they'll make a difference between this M1 and M2. But we can also show like these states are maybe very hard to reach, or it can be reached within this omega of C bar number of samples. So that's why there's an existent lower bound. Yeah. So this is why this appears to be a lower bound. The next thing is like, after we've done so far, this doesn't hurt the considerability coefficient or aggregated considerability coefficient. You can show like the considerability coefficient and the aggregated considerability coefficient are the same as the previous MDPM. So basically, after these steps, this finished the proofs. So any questions so far? Yeah, for any aggregation scheme. We can group the states as we want. So do you mean like actually what kind of aggregations do we usually choose? Yeah, yeah. Okay. So what does the aggregated states actually by us? It's like in the aggregated states, we'll, according to our construction, we'll make them to be of the same value. So that means that we'll create a hardness by distinguishing the states within the aggregation. So
carry through the rest of your proof. Will this one be a lower bound without needing the aggregation to begin with?
So I mean like for this aggregation scheme, so if we just don't consider the aggregated considerability, but we just calculate the standard considerability coefficient, so will that give a lower bound? Yeah, actually the answer is yes. Because actually one obvious aggregation you can do is you can aggregate each state them together themselves. So that's a way that you can arrive at something like the original aggregated, original standard or standard considerability coefficient. This is for both the upper bound and lower bound. It does. Actually, this is only shows it's a construction thing. Like, given the aggregated scheme of this previous MDPs, we can construct lower bound. So we can construct a lot of lower bounds based on the previous MDP and the different aggregation scheme. For every MDP and aggregation scheme, we can give a lower bound. So we can give another lower bound. We can give a lot of lower bound. And maybe some of the lower bound is maybe needed by us. So we can do this maybe. So like actually in the next section, we'll show how to use this to prove a lower bound for the MISO data. And in there, you can see like actually how we construct the aggregation scheme and how we construct the MDP. Yeah, you can say something like that. Yeah. So this aggregate is this is a construction lower bound. We didn't prove the lower bound for any MDP with aggregation scheme. Instead, actually, for every state, every MDP and aggregation scheme, we can construct another set so that it satisfies some properties, like this aggregation and conservability are the same, and it also appears to be a lower bound. Yeah, it depends on the, there's a, yeah. That's the same. Yeah. Okay. You mean this lower bound in the Foster et al. This previous? Yeah, actually, we can show like actually their lower bound is a special case of ours. Yeah, there's a in there. Yeah, but actually we are more general than their results. Like there is a special case of aggregation scheme. In their MDP, there's only 3 aggregated states, so we can get the lower bound. But here we can do maybe multi-layered MDPs with maybe a large considerability coefficient, large aggregated considerability coefficient. We'll show that this can achieve the admissible data's lower bound. Yeah. So we'll go through the exponential lower bound. How we do achieve the exponential lower bound for admissible data. This is admissible data across the H layers. So we have this theorem showing like there exists MDPs and this offline data distributions pi b, and this evaluation policy pi e, and also a function class, so that the considerability coefficient is small, but it still requires the exponential number of samples to do offline policy evaluation. Yeah. So the proof idea is very simple. We want to construct an MDP with an aggregation scheme so that the considerability coefficient is small, but the aggregated considerability coefficient is exponentially large. So if we can do this based on the previous theorem, this already gives a lower bound for the admissible data. So how do we do this? This is how we do this. So we construct these MDPs, which 3 states each layers, and we assign the initial distributions in this way. And for the policy to collect offline data, this policy pi b, we assign the transitions in this way. That is for the circle and the square with a half of probability goes to the next layer circle and square, and with a half of probability goes to the triangle in the next layer, and the triangle also always goes to triangle. Yeah. And based on this transitions, we can show like the occupancy measure of this policy pi b has the following upper bounds. Have the following lower bounds. Yeah, you can remember this three numbers will be used later. So next we'll construct the transitions under this policy evaluation policy pi e. So we'll always goes from the circle to square and square to triangle, and triangle always goes to triangle. Yeah. So this is how we get. So this MDP only has 2 actions, and this the first action is in this dashed line, and the second action is this evaluation policies. And for any policy pi, based on these transitions, we can show the following property. It's like this occupancy measures satisfy that it decays at least a half compared to the previous layers. So this will give another upper bound of the occupancy measure for every policy pi. So if you compare this with the previous occupancy measure of the pi b, we can show that the considerability coefficient is upper bounded by poly h. So this shows the first thing, the concentrability coefficient is small. So next, we'll do some aggregation, and we'll calculate the aggregated concentrability coefficient. So the aggregation scheme is we group the first two states together, and the third state actually alone. And we can calculate the aggregation transitions under pi b is in the following way. And the occupancy measure of, we only consider this specific aggregated states. The occupancy measure is bounded by 1 over 2 to the h. And the aggregation transitions under pi e is somehow in this way, with the property of this pH, this transition is transition probability is greater than 1 minus 1 over h. So according to this, we can show that occupancy measure is lower bounded by 1 over 4, 1/4. So based on this, we can show the aggregated concentrability coefficient is exponential. So we also achieved the second bullet. So that's how we prove this idea, prove this lower bound for audiovisual data. So we can show like there exists such MDP satisfy the concentrability coefficient small, but requires the exponential number of samples. Yeah. So any question for this? Yeah. Yeah. Yes. Yeah, definitely. Yeah. Because if you remember the previous theorem we showed, this is for any aggregation scheme and MDP, we can get a lower bound. So we can choose the aggregation scheme to be the aggregation scheme that can use a large aggregated concentrability coefficient. So that's the one that is desirable for maybe exponential lower bound. We can definitely choose a smaller aggregated scheme with a smaller maybe concentrability coefficient, but that's not what we want. Yeah, I can somehow say that. Except actually, for different aggregation schemes, the different class M is constructed. Yeah, for every aggregation scheme, we can construct this class of MDPs M. So for different aggregation scheme, we will construct different MDP class. Yeah. Yeah. So this is how we get this lower bound for the missile data. This is across the H layer. Yeah. So next, we'll maybe going fast for the trajectory data since I'm of insufficient time. So we have the similar results. Like when the offline data consists of trajectories, we still have the similar lower bound. So how we do this? We still want these two things. The first thing is like the trajectory data contains no more information than the visual data. The second thing is the concentrability coefficient is still small. So right now in this section, we no longer deal with the aggregated concentrability coefficient. So suppose this is a MDP for the visual data. We replicate every layers k times, and we'll make the MDPs of h times k layers. And among these layers, in the last layer of each block, we'll give the transitions as the previous MDP for the missile data. But within the block, we'll assign the transitions in the following way. This action 1 will directly go to the same state. And action 2 will go back to the missile data distribution. That is the data distributions of the first layers. So this is the transitions. So we'll do this for every layer. So what's the property of doing this? So we let this policy to collect the offline data to choose the action 1 and 2 with equal probability. And the policy evaluation policy always chooses action 1. We know that if among the offline data, if the policy chooses action 1 in at least one layers, then the next layers will go back to the next layers distribution will go back to the admissible data distributions, because actually every state actually will induce the same next layers. So actually this will erase the information that collected in the previous layers, and we can show like if we do this process for k iterations, we will remove the information with a probability at least 1 minus 1 2 to the minus k. So that means like the information is kept actually with a very low probability. So that's how we prove that actually this information of trajectory data is no more than the admissible data. And in the next thing, we can show like the conservability coefficient is small. So this we can prove that actually based on this construction, the conservability coefficient grows at most h times k times. So if we combine these two things together, we arrive at the following theorem, showing like this with the trajectory data, this still exists a hard case, so that we require the exponential number of samples. But in the meantime, the all-policy conservability coefficient is also polynomial. Yeah. So any questions so far? You mean, does this work for the examples in their paper, or is there? Yeah, as I just mentioned, like actually, in their paper, there is a special case for this aggregation scheme. Like we can construct an MDP with only 3 aggregated states, so that you can recover the lower bound for the Fossa et al. Paper. Yeah. So their paper actually is somehow maybe a special case of this general results. Yeah. And finally, we'll go through the upper bounds. So the upper bound will adopt the same algorithms in this Xie and Jiang's 21 papers. They proposed the algorithms called the BBFT. And we will ask like actually whether this aggregated considerability coefficient is a sufficient condition for the policy evaluation. And the answer is yes. So we consider this BBFT algorithms where for every, we define this, we'll calculate this value function in this way. And suppose that actually this, for any 2 functions in the function class, we can calculate the aggregation, one aggregation scheme according to these 2 functions. And we let this C bar to be the maximum value of all the possible functions in the function class. Then we can show like using this polynomial number of samples is enough to guarantee absolute accurate or absolute precision of line policy evaluation. So this term indicates that this C bar or this aggregated considerability coefficient is indeed the true thing for the offline policy evaluation task. Mm-hmm. Yeah, it's true. Yeah, actually, the previous lower bound, actually, I mentioned one property is like the aggregation scheme has to be compatible with the function class, and this specific aggregation scheme is compatible for the function class. Mm-hmm. No, actually, if you remember that the function class in the lower bound is also constructed by the learner. The function class is not given to the it's not given to this before. So we'll construct the function class so that the function class is compatible with the aggregation scheme. Yeah, actually, the thing is like one function class, they only give or maybe a function class of 2 items only gives one compatible aggregation scheme. That is the aggregation, we aggregate those states that with the same value within this aggregation scheme. Yeah, it's unique. Yeah. And here, actually, this is you have to do this maximum over the tuples of functions in the function class. And this is no longer an issue because the previous lower bound, the function class is only 2 items. Question? Yeah. So okay. Yeah. Let me briefly actually explain this. So this result also covers this Jiang's upper bound result. It also indicates a similar upper bound for the admissible data, even if we don't have have access to the trajectory data, but this is with the function approximation. This is recovers the upper bound for the importance sampling. Yeah. So we have this summary of the results. So we define this aggregated considerability coefficient, and we define this. We use this to prove a lower bound for general data, and we prove this for admissible and trajectory data, and we also prove an upper bound in terms of this quantity. So we also have some other results, but we'll skip this. Yeah. So the final thing is the open problems here. The open problem is like whether we can generalize this to offline policy optimization, and whether we can generalize this to online policy optimization. This is two interesting open problems. And that's all. Thank you very much. Yeah, so any questions?